How AI voice assistants really work, and where they fall short. Let me ask you something honest. Have you ever talked to a voice AI, Siri, ChatGPT, Alexa, and thought, how does it understand me so well? Or the opposite, gotten so frustrated you wondered how it could say something so completely wrong? If both have happened, today both feelings are going to make a lot more sense, because I'm going to show you what's actually happening inside these systems. And once you see it, you'll realize, no matter how smart an AI sounds, it's often built on a surprisingly simple misunderstanding. Let's start. You speak. Your voice hits a microphone. The microphone converts those vibrations into an electrical signal, which becomes digital data. So far, that's just basic physics. But after that, most voice AI systems bring in multiple models, one after another. The first model takes your voice and turns it into text. This is called STT, speech to text. Systems like Whisper, DeepGram, and Google's Speech API do this. They analyze the audio waves, figure out which sounds correspond to which words, and produce a transcript. The second model receives that text. This is where large language models like GPT, Claude, or Gemini come in. The model reads the text, analyzes context, and generates a response. In some systems, it can also pull information from the internet. The third model converts the generated text back into speech. Systems like ElevenLabs, Microsoft Edge TTS, or Google WaveNet handle this step. So you spoke, and you got an answer. But in between, voice became text, text was processed, a response was generated, and that response became voice again. According to OpenAI's published data, the old GPT-4-based voice pipeline averaged around 5.4 seconds of latency. And at every link in that chain, there was a chance for error. But here's the really important point. The number of models isn't the main issue. The main issue is this. Most of these systems don't experience the world directly. They mostly process a textual representation of the world. Think about it this way. You're talking to a voice AI. You walk across the room, getting farther from the microphone, and ask, I moved away, can you still hear me? What happens? The AI might say, your voice got a little quieter, or I'm having more trouble hearing you. Sounds reasonable, right? Even impressive. Wow, it actually noticed. But in many older systems, what really happened was different, because your voice had already been converted to text. What reached the language model wasn't your audio. It was the sentence, I moved away, can you still hear me? The model read that and reasoned, someone says they moved away. Voices typically get quieter when people move away. The logical response is, and it produced a fitting answer. But it may not have actually checked whether your voice got quieter, because in many systems, most of the audio data had already been reduced to words. Go one step further. You say, I moved 10 more meters away. Can you hear me now? The model might reply, I can barely hear you at all now. Why? Because it knows, textually, that sound fades with distance. It has learned patterns about the physical world. But maybe you never moved. Maybe the microphone is very sensitive. Maybe your volume never changed at all. The model may not have actually measured any of that. It may have simply produced the most likely continuation of the text it received. This matters enormously, because once you understand it, so much about AI falls into place. AI is often not experiencing reality. It's processing a representation of reality. In voice assistants, this gap is especially visible. You're moving through the real world, speaking, with events happening around you. But in many older systems, much of that got simplified in the conversion to text. Intonation, pauses, rhythm, background sounds, a lot of that disappeared. What remained, mostly, were words. And the language model tried to reconstruct the world from those words. Sometimes it got it right, sometimes it didn't. but the mechanism was the same either way. That's why AI can seem startlingly brilliant one moment and completely wrong the next. This is what's called hallucination. The model isn't lying exactly, it's generating the most statistically likely continuation of the input it has. Sometimes that's accurate, sometimes it isn't. And the model doesn't always have a way to tell the difference. That's why even when you ask an AI to look this up and tell me, you still need to be careful. It's interpreting what it finds. If there's ambiguity or contradiction in the sources, it may fill in the gaps with its own inference and deliver that inference in a confident, fluent, persuasive tone. Because voice assistants usually don't say, "I'm not sure, but maybe," they say, "Here's your answer." Now here's where it gets interesting. Precisely to address some of these limitations, some companies began developing a different approach. In 2024, OpenAI introduced GPT-4o. The O stands for Omni, a model that can handle different types of data within the same system. According to OpenAI's official data, GPT-4o can respond to audio input in as little as 232 milliseconds, with an average of 320 milliseconds, comparable to natural human conversation pace. The old pipeline averaged 5.4 seconds. This approach largely collapses the old voice-to-text to model-to-text to voice chain. Rather than just words, the model can now analyze features of the audio itself. Speaking pace, pauses, tone, emphasis, in some cases, background sounds. So even if you never say, "I'm sad," cues in your voice can be picked up. That wasn't possible in most older systems. Google is moving in a similar direction. Newer Gemini voice systems also process audio more directly. But here's the critical caveat. These models are still not perfect. New generation Omni models can handle volume changes, echo, and acoustic cues better than before, but that doesn't mean they fully understand your environment. Tests show they're sometimes cautious, sometimes approximately right. They perceive sound better. They don't understand the physical world the way humans do. The same applies to vision. They can look at an image and identify objects, but they don't always correctly interpret physical relationships or spatial context. Receiving data from the world is not the same as understanding the world. Most systems in use today still carry traces of the older approach. New Omni systems represent a genuine leap forward, but they are not flawless, and they likely won't be for a long time. So to summarize, older systems mostly work through textual representations. New generation systems are beginning to process audio and visual data much more directly. But there is still a significant gap between human-level understanding and today's AI. So what should you do when using these systems? Speak clearly. Use short, clean sentences. Provide context. Say exactly what you want. And when you receive important information, verify it. Ask, "How do you know this?" Ask, "What's your source?" Because a confident tone doesn't mean the information is correct. The bottom line: these systems are remarkably powerful and remarkably limited at the same time. Older systems mostly reduced voice to text. New systems are beginning to analyze the voice itself, but they are still far from understanding at a human level. They can generate responses, they can be helpful, they can sometimes be astonishing, but they cannot guarantee accuracy. Knowing that lets you use these tools far more wisely. Are we being deceived? No. We just often don't fully understand the tool we're using. Now you understand it a little better. If you found this valuable, subscribe. See you in the next video.